Hello AP Calculus students, welcome to our fifth video over topic 6.3, and I want to warn you this one's going to be a little bit tricky, and this is where some of the more complicated parts of Unit 6 come into play. And so I'm going to warn you in advance to not get frustrated and to think about pausing, rewinding, rewatching so that you can understand each of the steps that are going to be demonstrated to you in terms of working with an unknown number of subintervals. So no laying on the couch for this one, you guys. You want to make sure that you're very active and you're taking the notes and being attentive. So let's take a look at this example 5. What is it that we're talking about doing here? Well, it says here that we're going to take a look at a problem that doesn't give us the number of subintervals. So we have this uh, graph of f of x equal x squared. And you can see, even when I read the example, we're supposed to find the upper and lower sums for the region bounded by f of x equal x squared and the x-axis between 0 and 2. So I've got the shaded region here done. But like I said, I haven't indicated how many subintervals we're going to use. And so we are going to look at the value n. N is our number of subintervals. So notice I have both an upper sum and a lower sum column. And so we're going to go ahead and use those ideas. But before we do that, I want to make sure we can determine, as we did in the last video, which of these would generate a right endpoint and which of these would be generated by a left endpoint. And so if you start kind of thinking about drawing just a few subintervals, it doesn't really matter how wide they are. But if we want an upper sum, the only way that that will happen is if we capped off these rectangles by moving from the right side over to the left side, as you can see here. And then once we extend, you can see that you certainly have 3 different rectangles in that particular interval that are greater than the region under the curve. And you can probably guess lower sum is going to be a left endpoint. I'm going to show that in a bit. But let's focus here on just the right endpoint. So that's what we know the upper sum is going to utilize. Okay, well, what do we do next? Well, because the formula for the area of a rectangle is width times height, I would say we probably need to generate expressions for the width and the height so that we can multiply them. Now, the width formula is our good friend that we've seen many times thus far in this particular unit. B minus A divided by N. Well, in this particular problem, the B and the A are clearly given as 0 and 2. And so when you subtract them in the correct order, 2 minus 0 over n, you get 2 over n. And unlike our previous problems, we don't know a value of n. So this is going to serve as our width. So the very next thing that we do is then we focus on the height of each of these rectangles. And this is where things get a little bit more complicated. There is a formula that you can use for the height. And I'm going to go ahead and share that with you in this particular problem. And then I've got it in your notes on the subsequent page so that you can easily reference it later. But I want to talk about, as we move through this example, of why this function here is going to serve as the height. And it would be f of, f evaluated at your beginning endpoint, A in this case, plus the width that we discovered, 2 over n, multiplied by an arbitrary I that's just going to take on the values 1, 2, 3, etc. Okay, now why is this working for us? Well, if you think about the value of A in this problem, the value of A is 0. So that's not going to really result in much. And so really we just have f of 2 over n times I, or if you want to say 2I over n, that's perfectly acceptable. And what this is basically saying is that you just simply take your counter I and just start it at 1, start it at 2, start it at 3, and that's always going to tell you what the values are of each of these places that you're going to apply your right endpoint. I know that's probably really confusing. Like, what did he just say? For instance, let's say n was 5. It makes it a little bit easier when you have a concrete value for n. If n is 5 and we put I as 1, 2/5 is the first place that you'd have a right endpoint. Let's let n stay as 5 and let I go to 2. Now we have 4/5. That's the next place. 6/5, etc., etc. Now, we got very lucky in this problem because the left endpoint was 0, but there will be problems later on where that's not the case. And so you always have to start your expression counting from whatever happened to be the very far left. Most of the time there are 0, but sometimes you might have something besides 0. Now, from this point on, things will kind of get a little smoother for a little bit because you have to evaluate the function f at 2i over n, which means you're going to plug 2i over n in for this x. You're going to square it. So that's going to give you 4i squared over n squared. Okay, so what do you do with these things, you might ask? Well, the formula for finding the area of a rectangle is multiplying these two things together. So you could take, I leave a little room here, you could take your height and you could multiply it by your width. But what you gotta have to remember here is the fact that you're going to add up a whole bunch of these particular expressions. In other words, I is going to start at 1 and it's going to go all the way up to how many ever shapes that we have in this problem, which in this case is going to be n. Okay, hopefully that makes a little bit of sense. We'll see. So from this point on, what you're going to do is simplify this just a little bit. Now, there's one thing that I want to consider at this point, and I'm going to go ahead and invoke this right now. I want to go ahead and make the statement that let's eventually let this n grow to be very large. And I know I didn't leave quite enough space here, but I really want to consider the fact that this n could be as high as infinity, which would be a great thing because that would give us a very good approximation. So here's what we're going to do with this, you guys. We are going to simplify. So we're going to keep that limit statement. We're going to keep this summation. And we're going to just multiply this and get 8i squared over n cubed. Hopefully you see the arithmetic or the algebra behind that. Now we're going to work this summation. We're going to use our summation properties. Remember the very beginning of this unit, I did a video series for example 1, 2, and 3. We talked about how you use summation notation. Now that's going to kind of attach to the newer ideas. So what I would suggest here is that anything that is inside of this summation that does not contain the letter I, move out to the front. Now why? Why is that something that we want to do? Well, this summation is only going to affect values of I. You can see that the lower index starts when I is 1, then I is 2. So if you have an I in it, you're going to be changed. But if you don't have an I, you're just a constant for all intents and purposes, and you can move out in front of the summation. But I don't want to be too crazy with this and move it out in front of the limit because the limit will affect things that have an n. So that's how you always want to recognize that. Now at this stage, again, I draw your attention back to the beginning of the notes where we talked about summation formulas for various things like I and I squared. Well, you're going to be able to use one of those at this point. And the summation formula for I squared happens to go n times n plus 1 all over 2n plus 1 all divided by 6. And here we go. We now have an expression that if you can take the limit for, you are going to get the correct answer. Now to take this limit, This is where we can really save a lot of time. For instance, I could do some very quick simplification, I think, on this and call this 8 a 4 and call this 6 a 3. And then I can cancel n over n cubed, where I would have maybe an n squared on the bottom. And then on the top, I would have n plus 1 times 2n plus 1. Well, if you remember your rules for finding the limit as n approaches infinity, all you have to do is compare the degree of the numerator with the degree of the denominator. That's going to be a very important limit idea that's going to come to fruition. So in order to make this happen, you can think of it, let me do this. You can think of this numerator as being something like this. If I were to multiply n times 2n, I know I would get 2n squared. And if I multiply that by 4, I would get 8n squared. And then after that, I just get a bunch of stuff. But I don't really care what that stuff is because that stuff is just going to consist of n's to the first power or constants. And so I'm okay to stop right there. The denominator, well, nobody's going to argue that the denominator is 3n squared, right? That's all that you're interested in, because since these powers match, you just divide the coefficients and you have an answer finally of 8/3. That's going to be your upper sum limit for this problem. Now let's take a look at the lower sum. The lower sum in this particular problem, if you'll allow me to redraw some rectangles in just at random spots, the lower sum is going to consist of a left endpoint approach, as you can see here, right? So we want to think about that as our procedure. Now, how does that differ from, let's say, a right endpoint? Well, it differs just a little bit, and it does cause a little bit of a headache. Let's see what I mean. So the width is not going to change. I have got great news there. It's still b minus a over n, which is 2 minus 0 over n, or 2 over n. The height is going to be f of, okay, well, that sounds familiar. A, that sounds familiar, plus b minus a over n, which in this case is going to be 2 over n. Let's just go ahead and write down the exact procedure that we have. But now things are different. Because we're using a left endpoint, we have to take that I and we have to slide it over to the left in order to call it a left side endpoint. And so you're always going to use an I minus 1. And that's usually the question that's most commonly asked. Is it always I minus 1 for the left? That's how we're going to set it up, yes. Now the problem with this is, yes, we do know that a is 0. That's wonderful. But this 2 over n times I quantity minus 1 is a bit, shall we say, more inconvenient, for lack of a better word. Because if this is what we have left, we're going to have to plug that in for this x, and we have to square all that stuff. Yeah, I know, not fun. If you square 2 over n, you get 4 over n squared. But if you square I minus 1, you have to expand out the polynomial or the binomial I minus 1 times I minus 1. And the FOIL, if you want to call it that, is I squared minus 2I plus 1. Wow, it's pretty intense. So what is our area going to be in this problem? Well, we're going to take the limit as n approaches infinity, because that would be what our ultimate goal would be, to put as many of these shapes in as possible. And we're going to take the summation as I goes from 1 to n, and we're going to take our height, which is this expression right here, and we're going to multiply that by our width, which is 2 over n. And like I said, this is a long process, a long video. At any point, if you need to pause this, kind of catch up, take a breath, please do so. This is one of the more complicated things that we are going to do probably in the entire course. Now, from this point on, all you need to do is rewrite the summation expression in such a way that you can start using the summation formulas. What that means is anything that does not have an I needs to come out in front of the summation. So I'm going to keep that limit in there. I'm going to factor out an 8 over n cubed because none of those things have an I in it. And then this thing is going to be multiplied by the summation of basically this gray underlined expression. But I think what I'm going to do is take note that as I write this expression, I know that there are formulas for each of these terms. The I squared, the minus 2i, and even the plus 1 have formulas that you can use to rewrite those. You're going to find out that you have to do a lot of writing in these problems. You have to do a lot of copying a limit statement down, maybe copying this 8 over n cubed back down again, but we're getting pretty close, you guys. The summation of I squared is a formula that goes n times n plus 1 times 2n plus 1, all divided by 6. I think we used that in a previous example. We will subtract. Now, for the summation of 2 times I, the 2 drops down, and remember the summation of I is that n times n plus 1 all divided by 2. Now, if you forgot those properties, you can just flip back in your notes to be reminded of them. And then lastly, the summation of 1 is just the summation of a constant, which gives you constant times upper boundary, which is n, so 1 times n is n. So we close the parenthesis and then we close the bracket. And now, as soon as you feel comfortable taking this limit, boom, you've got your answer. The problem is this limit can be a little pesky until I think you have a nice common denominator. So I'm going to really encourage you guys to go that route. So my whole denominator here is likely going to be an n cubed along with probably a 6. Now the n cubed, I should note, is just really a part of this 8 over n cubed. So how about, to avoid maybe any confusion, maybe it would be better if I leave the 8 over n cubed out in front on second thought. I just don't want you all thinking that you've got to start multiplying these things by n cubed. So we definitely don't want to do that. All right, so our first expression here. Well, if we were to start foiling things together, we would have a 2n squared multiplied by an n, which would give us a 2n cubed, right? And then we would have a bunch of other stuff. Now look how informal I'm going to do this. I don't think I have to be so concerned about that other stuff because I only want the highest degree value of n, which I know is going to be a cubed. In this second term, I already have a 2 there. I need this to be a 6, so if I multiply the top and the bottom by 3, this becomes 6n, and if I distribute, I just notice that this is just going to become a 16, a 6 times n is going to become a 6n squared, right? Which really does not affect the overall power here because I still have cubed. And then of course over here with this n, I'd like to see him have a denominator of 6, which just means he's just going to be embroiled in multiplying by a 6, right? So the point I'm trying to make is that the only things that really matter in this problem are this term right here, of course this guy and this guy because they're going to be multiplied through, and that term. Because when you find the limit as n approaches infinity, all you need to do is take the coefficient of the highest degree term on top, which is 16, take the coefficient of the highest degree term on bottom, which is going to be a 6, and by the time those reduce, you get, oh, well, what do you know? 8/3. Now, here's the great news. If you were to look at these two approaches, the blue approach and the red approach, and I said, all right, guys, you got to pick the one that you like best, and I'm going to let you use that approach for the rest of the course. I doubt too many of you would say, oh, I want to do the red. All right, the blue's bad enough, right? You have to choose one or the other. And so the point I'm trying to make is that if you're using a limiting process where you let n be an infinite number of rectangles, there is no way that you want any part of setting this up with a left endpoint. And the reason is because you know that you're going to get the same answer either way, so why don't we do it the easier way, which is with the right endpoint? It's still pretty rigorous, but you can get a correct answer a little bit quicker. Now, I'm not going to lie to you. You can't get good at this unless you practice it. Good news and bad news. The good news, on the AP exam, will you ever have to do something as rigorous as this? No. However, you may have to recognize what kind of setups are associated with various functions. So you kind of have to work backwards from a particular summation setup to say, hey, what function were we trying to find the area under? And what were the boundaries? And et cetera, et cetera. Okay? So that's what's still on the horizon. We still have quite a few very intricate things to discuss. Some of the videos are going to go longer. Some of our lessons are going to go longer. But you're in the dog days of the beginning parts of integration. We just have to work hard. All right. We thank you for joining. We'll see you next time.